There are several reactions that we can do on epoxides, or starting from an epoxide. Now, this is in contrast to a typical ether. So in most cases, an ether is not reactive, or in a lot of cases. So for example, if we just went with diethyl ether, this particular ether is not reactive towards alkoxides, which are fairly strong in terms of nucleophiles. So we're actually going to get no reaction in this case. Now, that's not necessarily a bad thing. We don't need everything to react. And in fact, this is one of the reasons why these often get used as solvents. When we're performing a reaction, it would be nice if our solvent did not steal all of our reagents, and instead we could react it with what we want. So ethers often get used for that. An epoxide is just kind of a special ether though, that has a significant amount of ring strain. So even very mild conditions can open epoxides. So here's a very simple epoxide, and let's look at some quite mild conditions. We're going to add some sodium chloride to this and some alcohol to help get this dissolved. And we can actually have a SN2 reaction on this to open it up to make this chlorinated alcohol. And the above reaction with the sodium alkoxide, that will definitely open up our epoxide ring. And I think in this case, I'm going to draw the mechanism just so that we can see what's happening. So we've got our alkoxide base. We're going to have that attack one of these carbons. They're both the same. That will open up the ring. And then we can make this. So here's from our alkoxide base. And then the negative charge. Let's see here. I think I'm missing a carbon. Yes, I am. That's better. So our negative charge from here is right there, and then we'll need to have some workup step, and since we have some methanol in the solution, we'll use that to take a proton from. And we're going to steal the proton from there and form our product. Which in this case is an ether and has an alcohol on it as well. And again, this is an SN2 mechanism. Now, again, because of the ring strain, there are a lot of reactions that we can do on this. We could employ either a Grignard or an organolithium reagent. If we do, we will need to perform an acid workup when we do those steps. The reason for that is that we'll need to operate in aprotic solvents in order to not destroy the Grignard reagent or the organolithium. So we could do this one, say the phenyl magnesium bromide. Or we could do the corresponding organolithium reagents. And we will dissolve this in diethyl ether. Again, for the same reason up here, we won't have a reaction with it. And during that first step, what we're going to do is we're going to have this carbon negative add to this position right here. And we will form this part. Now, we're going to have a negative charge on this that's left behind because we don't have any hydrogens here in the solution that we can easily steal. So we'll have to do a second step after this first bit of the reaction is done, and we'll just add some acid to the mixture. It doesn't need to be a particularly strong one, just some inorganic acid, and then after that second step, we'll turn that negative into a hydrogen because that will protonate the alcohol and we'll be able to isolate this product then. But when we have these Grignards or the organolithium reagents, we do need to add the acid workup step just to get that proton back on the molecule there. We can also react this with a sodium cyanide. This is a good way to add an additional carbon onto the molecule. In this case, we can dissolve it in water, so that's where the proton would come from there. We could react it with an alkyne. Well, a terminal alkyne. First, we'll need to prepare the nucleophile. So we will deprotonate this hydrogen. One of the ways that we can do that is with sodium hydride. And this is a fairly strong base. So we'll generate hydrogen gas and we'll make this deprotonated, so it'll be carbon negative there. Next, we can add in our epoxide. And then, similar to our Grignard reagents, we will need an acid workup step. So we will need to add some acid. And after all of these steps, we should have added an alkyne onto our epoxide. And again, we still have the alcohol there. Now, the steps were we deprotonate the alkyne. We have the SN2 attack from the alkyne onto the epoxide. That opens it up. And then the last step, we're just putting a proton on there as part of the workup. Now I have one more reaction that I think I can squeeze on the page. And that's where if we add a hydride reagent like lithium aluminum hydride or sodium borohydride. So this is a source of H negative, and then we'll need an acid workup again after that step is complete. So we'll have our H negative, that's a nucleophile, could come in and attach itself here, open up the ring, and we would have, hang on, a proton added to that carbon. So I'm going to explicitly draw it in, even though We don't always have to do that. And then we'd have our oxygen there, and it would have a negative charge on it, but of course we have to add our acid workup to convert it into, in this case, ethanol. So as you can see, there are a lot of reactions that epoxides can undergo if they're a substrate. In the next video, we'll talk about what the selectivity of attack can be when we're using epoxides. In these cases, we all had symmetric epoxides. Let's look at a case where we have asymmetric ones.